Alright, have you ever wanted an example of a function where you take the derivative with respect to x and y, and then with respect to y, then x, and you evaluate at a point you don't end up with the same thing? Well, here's an example. So let's jump right in. For part A, we want to show d2f and d1f. So now this is not like one of those previous exercises where we're actually able to plug in like part of it and help simplify our formulas that way, because here we're taking the derivative with respect to y of f of x comma 0, so y is plugged in, so you have to find, what we have to do here is we have to find the total derivative of f. Or we need to find d1 of f and d2 of f, and then evaluate at x comma 0 and evaluate at 0 comma y, and that's how we're going to get part A. So the tricky part of this is we've got this x squared minus y squared over x squared plus y squared. That's the hardest part. So let's actually start by evaluating this. So we have d1 of x squared minus y squared over x squared plus y squared equals, can I fit this? I'm going to try fitting this on. No, I probably shouldn't. Okay, so we have low d high times high d low, so low x squared plus y squared times the derivative of what's on the top minus the top times the derivative of what's on the bottom. And we're going to divide this whole thing by the bottom squared. And so this is going to be equal to, let's see here, so here we get x squared plus y squared and d1 of x squared, so that's going to give us 2x. Then we subtract x squared minus y squared, and then d1 of this thing, well, we're also going to get 2x. And we're dividing by x squared plus y squared, this whole thing squared. And so, let's see here. What we can do now is, we've got an x squared plus y squared 2x. So if we multiply this out, we've got a factor of 2x in both of the terms in the top, so we can just take 2x, and then we have x squared plus y squared minus x squared minus y squared. And we're dividing by x squared plus y squared squared. And then finally, so when you take the x squared and you subtract x squared, that's going to be 0. If you take y squared and subtract minus y squared, we're going to get positive positive 2y squared. So we're going to end up with 4xy squared on top and x squared plus y squared quantity squared on the bottom. And we're going to get a similar thing if we evaluate d2 of this. So if we take d2 of x squared minus y squared over x squared plus y squared, we're going to get x squared plus y squared, and now I'm just going to straight away take the derivative with respect to y of x squared minus y squared, which is going to give us minus 2y because of that minus sign. And we're subtracting x squared minus y squared, and then d2 of x squared plus y squared, this will be positive 2y. And of course on the bottom we've got x squared plus y squared quantity squared. Okay, so now what's going to happen is we've got a negative 2y that we can factor out here, and then in the first term we've got an x squared plus y squared, and in the second term, because we're putting the minus sign next to the 2y, so we're going to add x squared minus y squared. And then on the bottom again we have x squared plus y squared quantity squared. And then here we can simplify this. We'll end up with a 2x squared, and then the y squareds will cancel, so we'll get minus 4x squared y over x squared plus y squared. Okay, so that's probably the most computationally intensive part of this exercise. So now let's move on and actually get into d1 of f. So d1 of f is going to be d1 of, so remember, this is d1 of xy times x squared minus y squared over x squared plus y squared. So we can think of this, the fraction part as its own thing, and the x times y as its own thing. And so here we're just using the product rule. So when we use the product rule, we're going to take the derivative with respect to x of the first part and evaluate the second, or keep the second part the same. Then we're going to keep the first part and then take the derivative of the second part, which we know to be, well, the derivative of the fraction part with respect to x, we just calculated that to be 4x, oh no, oh come on, there we go. Alright, 4xy squared over x squared plus y squared squared. Now for this part of the exercise, what we want to know d1f at 0 comma y. So d1f at 0 comma y, well, when we plug in x equals 0, the second term, we have a 0 there, so that automatically drops out. In the first term, we have y times x squared, y times 0 minus y squared, 0 plus y squared, and this is going to give us negative y. Because the y, well, assuming that y is not 0, we can cancel, and if y is 0, then, well, then, it's 0. Don't worry about it. And then, so there's that. Now d2 of f. Okay, so that's what we wanted for d1f of 0 comma y. Okay, so that's good. Okay, this is bugging me a little bit. What about y? Well, when y equals 0, we can't just straight up plug in y. Well, if you take the limit as y goes to 0, wait, no, we know what it is at 0. At 0, it's 0, right? Yeah. If you do the limit, it ends up working. All right, d2 of f. So now this is going to be d2 of xy times x squared minus y squared over x squared plus y squared. So we're going to get one more. So this is going to give us x times the fraction, and then we're going to add x times y, and then we're going to multiply by minus 4x squared y over x squared plus y squared, quantity squared. And now we are evaluating what we want d2 of f at x comma 0. And when we plug in 0, the second part drops out, and the first part also? No, y equals 0. When we plug in y equals 0, second part drops out, first part becomes x times, to get x squared minus 0 over x squared plus 0, and so this just gives us x. And that's what we wanted. Okay, so that's part A. Now for part B, we want to evaluate the second derivatives. So now d2 of f of x0 equals x. So this means that if we take the derivative of this equation with respect to x, then d1 of d2 of f of x0 is going to be d1 of x, which is just 1. But d1 of d2 of f is just d1 comma 2 by definition. So d1 comma 2 f of x0 equals 1. And d1 of x0, d1 of f of 0y equals minus y. This implies that d2 of d1 of f of 0y equals d2 of negative y, which is negative 1, and therefore d21 of f of 0 comma y equals minus 1. Hence, d1 comma 2 of f of x0, f of 0, 0 is going to be 1, and 1 is not equal to negative 1, but that's what you get when you evaluate d of 2 comma 1 at 0 comma 0. And that's exactly what we wanted to prove. So we are now done with the exercise.